for the separator sizing. I have around 15 years of experience into process engineering, varying from heat transfer, like a heat exchanger design, then the separators, PSVs, flow air, blowdowns, system engineering, like for operations as well as FPSO, then wiring for offshore platforms, onshore refineries, and other chemical engineering aspects. I have worked into green hydrogen as well. At the same time, I have worked for greenfield as well as brownfield projects. I do conduct various trainings for under the chemical, and let's begin with this. So before starting, just have a uh, quick suggestion, or I'll say a quick thing for you. At any moment, if you thought you are not audible, like I'm not audible, or you're not understanding anything, please raise your voice. Please be attentive to any particular topic or any point. If you are not getting, then please raise your hand, so that for us as well, or for me, it will be happy to introduce you or to define your requirement, or we can go back to the particular session again. Okay, so let me share my screen. Okay, is my screen visible to you all? Can anyone raise?
Yeah, yes, sir.
Yeah, thank you.
Yes, sir.
Yeah, yes. So, any one of you having any experience into design of separators or working into operations where they have come across any solutions or something like that, then those inputs will be beneficial to all of us, because those guys will be knowing how it is operating, how we are designing, or what are the difficulties they have faced.
So
So we'll
you
try
can
to
full
cover as
screen.
well. Yeah, I have shared. This is a PDF file actually. So
Sir, you can like do the full screen for this presentation.
yeah, you can see now.
Yeah, yeah.
Yes. So if my voice is not audible or clear, just uh, talk in between. Okay. So let's start our journey. Okay. So as everyone knows, being a chemical engineers, we have majorly come across many unit operations, unit processes, and for any plant, whether it is a small scale, whether it is a pharma, chemical, a refinery, offshore, onshore, or FPSO, we need a vessels. We need the vessels, whether it may be a tank, whether it may be a FRP tank, whether it is a vessel, but all these items are just there to hold the liquid, to process it, or to send the raw product for the processing, or to store the produced products in the form of liquid majorly, or in the form of liquid which has been converted from the gases. However, we majorly do not go for storing the compressed product gas. However, we majorly convert them back into liquid in some cases. If we go into these details, like any of the vessel or any of the tank or any of the things which is holding the liquid, but how to separate these separators? Separators are nothing but these are the vessels which are designed for the higher pressures. Higher pressure means it is more than 3.5 bar gauge or 3.5 kg per cm square gauge as per the ASME rules, and those are there to just separate the two phases or three phases of the feed. The feed may be the output of any reactor. The feed may be the output of any reaction. The feed may be coming out of the compressor. The feed may be coming out from the well, which is the crude oil, along with it is carrying water, or water, liquid, and gas altogether. These are typical feeds what we need to separate into each immiscible phases, like air and condensed moisture. We need to separate, or we need to separate the condensable liquid or condensate from the compressed gas. So we need any of the vessels, and that is called as separator. Separators and tanks are distinguished by their volumes, their design criteria, and their orientations. Rest all, everything goes same. When we go for tanks, tanks are majorly large volumes. Okay, this may be a floating roof or fixed roof. Those are designed as per API 650, 620, and the design pressure is not even costing zero point 0.5 inch of water column. However, when you come on the separator sizing, separators may be the feed separators or the inlet line separators or compressor knockout drums. Those are small volumes as compared to the tanks. These are coming in the orientation of vertical or horizontals or may come with the boot. However, the design pressure of these separators much more higher than what we have for the tanks. This is a quite distinguished a separate line between the two segments where we store volume. Majorly, we use tanks for separate the oil and liquid, and where the separation occurs because of the sedimentation or because of the gravitational force. However, when we have separators where continuous feed is coming, separation happening, feed is separating into the gases, uh, light oil or a light product feed or heavy waters, and this is continuous. Whereas in case of tanks, we are giving much residence time. Okay, that is the major we can say. Now, when we talk about any separators, separators are the main crucial part, and we design the separators by using API 12J. API 12J gives you an idea about how to design separators, what are the things we require for any separators. And this is the basic guideline outlined by the American Petroleum Institute. Majorly separation is happening because of the gravity, or you can force the separation by using the centrifugal force, or the separation may occur when the small particle coalesce together and form a larger droplet and may rise from the water to the oil part or oil to the water side. The same way, when we have any of the separators which is coming out of the what we call it as well, or any of the separators when we have a very high vapor volumes, then based on the vapor or gas to liquid ratio, we define what kind of orientation we require. When you have very high concentration of or very high flow rates of gases, then we generally go for verticals. Whereas when we have a very high quantity of liquid, then we generally go for horizontal. That will come to that later in this presentation as well. API is the major one, which gives you the idea about or outline the requirement of any particular separators in the chemical industry. Whereas we have some GPS standard, gas processing and separators or separators on a gas processing and distributor association, something I forgot the name, GPSA we generally call it as. At the same times, we have some standards from, we have Shell DP as well as ExxonMobil also have their own guidelines. Even ADNOC has defined their own requirement. However, these all requirements follows some part for API 12J or from the GPSA itself. Okay, that is the main what we call it as the Bible for particular this requirement. Okay, GPSA is generally a gas processing and suppliers association that gives you more detailed or rigorous idea about these separators. They have various volumes or modules based on the each of the topic in process industry. Okay, as I said, separators are being used to separate the feed into various phases, whether it's the gas, liquid, or heavy liquid, generally water. But when we have a three phases altogether, we call it as three-phase separator. When we have two phases, we call it as two-phase separators. When we have an feed separator, or generally the separator, a feed inlet separator in the offshore platforms, it comes with some kind of sand in the feed as well. So we use some sanding devices or consideration for that as well. However, majorly our common application for this one is the liquid hydrocarbon, like to recover majorly a liquid hydrocarbons, and then to degasify, like we have to remove any of the trapped air or any trapped light liquid from the high density fluid, that is majorly water. That is in case of three-phase separator. This is a typical example. Generally, if you have seen any offshore platform where you have the feed which is coming from the wells, that is the crude oil, which is having the gas, oil, and water flowing together. The feed is directly coming from the choke walls, and after choke walls, through production headers, that has been flowing to HP separators. This is typically a horizontal one because it has three phases and high volumes. And whether it may be a submerged weir all the time, or there may be a no weir that we'll see later. This is operating at high pressure. That's why it is called as separators. The lighter liquid is being taken to the next separator, that is called as IP separator or intermediate separator, then the low pressure separator. When we have a pressure reduction here, because of the pressure change, the liquid will flash, the lighter liquid will flash, and any trapped gas will separate it and it will flow back to the compressor. The same way it goes to the LP separator, then it goes for the degasser, or then after treatment it goes for the storage. However, the recovered gas is goes to the compressors and then it will be fed to the compressors. It may be go for main injection compressor or main gas compressors or even some of the export compressors as well. Generally, when we have or when we are defining any separators based on its pressure, then it is called as high pressure or intermediate or low pressure separators. General typical guidelines says that when you have any of the separator which is operating around 1500 psig, then this is called as HP separators. Where it when we have it is operating around 750, this is a general referral or general guidelines we use in industry. However, generally what I seen, HP separators are operating in the range of we generally call it as 30 bar gauge or 35 bar gauge as well, and this has been defined based on the quantity of feed and quality of the feed. Sorry, someone is talking about. Okay. There are various. Sorry. Uh, do you have any question? Uh, Mr. Prashant, you have any question? Okay. Might be mic on. Separators are typically a critical one because this give you the primary separation, whether it may be a separation of the two phase which is coming from the reactor or any of the thing which you have, or suppose if you have any distillation column followed by a air cooler followed by a trim cooler, and then you have a separation. There also we require separation to separate the gases, that is uncondensed gases, then a lighter product, that is a main product that will go as a reflux as well as a product, and to remove any of the higher volumetric or high density fluid that is coming to the top of the distillation column that we use to separate. That is why a separator is a typical one we require in industry. At the same time, we require separators towards the compressors. The compressor, each compressor stage inlet is attached with a separator which separates any of the liquid particle going to the compressor section. If higher volume content or saturated gas with any enrichment of the liquid particle goes to the blades of the compressors, then it will damage the compressors. And compressor delivery is critical, as well as the cost of the compressor is very high. That's why the sizing of the separators is generally critical in case of compressors. So we'll see this all together. As we said, horizontal separators are generally preferred when you have very high liquid rates, or when you have a very high three-phase fluid into the system, or when you require high residence time for the separations. Then it is preferred to use a horizontal separators. Generally, if you have oil, water and gases coming together from the well, then it will goes to the first three-phase separators. Here you can see it has inlet. It is typically a vessel. Separator is nothing but the vessel, and being a chemical engineer, you have to size the dimensions. What would be the ID, length of the separators, then what are the level settings, and that's how this is gives you a dimensions of a vessel. So it's done with the sizing. But to design or to estimate or to find these dimensions, you have to follow different rules, codes, standards, or some of the company guidelines as well. Or sometimes general people do not give you any idea about this. So you have to use your own company standards or what it has been given in the GPSA requirement. So any separators is having inlet device, some kind of separation media that is been there to enhance the separation. You can see the oil and emulsion which is at the top and the water is at the bottom. And this is called as weir. That is giving or creating a separation within the vessel so that the lighter part of the feed will flow over and that will be separated. However, the remain media or the remaining volume is being used to allow the separation between the lighter and the heavy fluid. However, when we talk about the gaseous will come together. There is a mist eliminator that is nothing but a nest of a wires that will allow or reduce the entrainment, and then it will go back. The pressure in any separator is controlled by gas flow. It's not about the liquid volume or liquid quality or quantity. Any separator operating pressure is designed by or defined by or maintained by the gas pressure as well. Three-phase separators are majorly used when you have very high liquid volumes or when you need a clear separations. However, it has some other advantages too that we'll see. When you go for vertical separators, vertical separators are when you have a very high volumetric flow rate of gases when compared to the liquid. Sometimes you might have seen majorly the feed is gaseous, but still compressor have been given with the separator, and in that cases you have to consider 2 to 4% mass basis of incoming flow as your liquid volumetric flow entering to the systems. This generally 2% is being utilized or being the criteria comes from the flare knockout drum sizing as per API 521. However, it has been widely accepted across the industry, and generally people use 2 to 4% of incoming mass flow rate as a liquid flow rate while sizing the separator. Okay. Generally, in any separators, you will see the mist eliminator or other devices that we'll see down the line when we go for just to enhance the separation capacity or enhance efficiency of separations majorly. Any separator we used to design, or we design any separator for giving a residence time and to have a clear separation between the phases. Okay, that is the basic principle what we have. There are some other uh, methods of separation as well, like what we have on the screen, that is called as cyclone separators. Cyclone uses the centrifugal force, and you have the entry of the feed is tangential, so that any higher density fluid will flow across the surface, it will try to stick and it will fall down, whereas the lighter fluid will go from the center outward. These are generally used when you have any kind of solids present in this. At the same times, when you need, or when you observe that there is a enrichment or entrainment of the liquid particle through the gas, we use cyclone devices to avoid the carryover of the liquid particles. That we'll see in this next things as well. There are some other separator media as well, like filter separators. Filter separators are generally being used at the inlet of GDUs or inlet of amine systems or inlet of the membrane systems, because where we need a clear gaseous flow to the systems, and the separation requirement is in the form of microns, like 10 microns, 30 or 100 micron fluid particles, or any of the piping material that has flow along with the gas towards the membrane or other systems. We cannot tolerate those, so we use these kind of separators, the filter separators, in line in the separation. These are again the separations. In this cases, separation may be happening in two parts. The lower part, if we have this as a vertical, the bottom part is the main separator, where separation is happening because of the gravity, whereas in the upper chambers we have some filter media that is generally called as cartridges, and there the separation is happening through the cartridges because of the pressure force. This is what we have generally, that is called as gas coalescers or the cartridges, again the same, and that is being used at the inlets of the glycol dehydration or amine treatment. What I was talking about is this one. In this, the separation is happening because of the gravity in this section, whereas in upper section coalescers, or what we call it as the separating media, the cartridges, where because of the pressures, when they pass, the gaseous particle pass through this coalescer, the liquid will coalesce. They form a tiny uh, molecule or tiny liquid drop. They come together, they form a higher density or higher volume, and then they fall down. In this one, the initial separated liquid is separated at this point, where in upper chambers it has been taken out from these sections. So this is the two-stage separations what we have. Yes, knockout drums. Knockout, as the name suggests, is to remove any liquid droplet or any gaseous part to be separated from the liquid. Uh, Knockout may be used for uh, different namingly or use at different sections. A flare knockout drum, or knockout drum for the compressors, or generally a scrubber. Scrubber is again the same, where we contact the gases which is carrying some impurity along with them with the any of the liquid which is having an affinity for that carried material, and that's how we design the scrubbers. And here we do not follow a major separation rules what we have for others. However, in case of flare knockout drum, they have their own guidelines. At the same times, the seal device what we use between the flare knockout drum as well as the flare tip, that have their own rules for the API 521. And general GPSC equations are not followed at that point. Okay, so when we have or how to define what type of separation we require, whether we have to go for cartridges, we have to go for normal separators, or what are the fluid parameters we require for these applications. To define any separators, whether it is a feed separator, whether it is compressor inlet separators or intermediate separators, you require various details about the flow, whether it is operating pressures, temperatures, gas volumetric or the mass flow rates, densities, viscosities. The same with the lighter fluid, that is the oil, as well as the same with the heavy fluid as well. At the same time, generally, it is great to have an information about water solubility, any entrainment capacity or capability it has, any traces of impurities, whether it is carrying any sand, so that we can give some arrangement for that as well. And when you have any details about all these things, we can easily design any kind of separator for that. Once you have an idea about the code requirement, applications, physical thermophysical properties, then it's done. You can design any of the separators in an industry. Separators, now from here onwards, we'll majorly go into details about the separator sizing. So do you have any idea? Till time what we discuss is majorly about the separators, what they do, how the selection sizing has been, or majorly the selections, or what are the type of the separators what we have in the industry. So do you have any issue in this one, or anything we can go back and we can discuss a little bit more in this? Anyone? Okay. So we'll see uh, how the separation actually works. So separation is nothing but we are separating something, majorly a gas and liquid. In case of two phase, for which we are conducting this session, we have to separate the gas particle or the liquid particle majorly, which is having higher density than gases, from the gas stream. And to design the separators, there are various factors affecting on the liquid molecule or the liquid droplet which is there in the gaseous stream or the feed stream. The separation is depend on the droplet size, how much size of the particle of the liquid is flowing along with the gas. This droplet size is based on the operating pressure, some inlet piping requirement, as well as the fluid properties. Now, if the fluid is flowing to any separator, then suppose let me draw one quick example for you. How I'll tell you, or I will try to define you how the droplet has been formed. Suppose you have this vessel. My drawing is not clear that much, so be understand or be adjust with this. Suppose your okay. Suppose this is the feed line what you are having, which is coming from the top. Then it's changing its direction at this point, coming downward, changing its direction, and then it's coming to the separator. When you have any kind of two phase, at this moment at this moment, the fluid is changing its direction, and that's how they strikes at this point. They strikes at this point and creates a droplet, or they may give you a break in the droplet size and creation of new droplet size. Or at the here, because of this uh, change in the elevation, the liquid will try to coalesce, sudden fall of liquid, and then the change in direction. This will also create change in the droplet size. So you have to be very cautious while designing the separators. At the same time, you have to look into the inlet line conditions as well. There shall not be any such a case that your droplets form so tiny or they form any mist. So you have to be very cautious in these cases. The factors that may allow or they may reduce the droplet size is high gas velocity and the density, or liquid surface tension. That is the liquid surface tension of any liquid which is flowing along with it. Any shearing happening, suppose you have an control wall or any of the wall, and if your fluid is passing across it, that will create a shear or a resistance to the flow, and that will give you a change in the droplet size. In case of liquid, you generally use agitators or static mixers that will be stabilize the fine droplets. But you have to ensure that when you are designing any of the separators, your inlet line is minimum 10D. You do not have any bend or elevation change or any wall located within the 10D, that is the 10 times the diameter of inlet pipe. There shall not be any bend or any wall or pressure reducing element like flow meter, generally not flow meter, but orifice or anything which can create a shear difference in these fluids. Here is the typical size distribution patterns what we have from the GPSA. Okay, so now suppose we go into much deeper now. Okay, let me draw and separator for you. Suppose let me size this way. Suppose this is the pipe you have at the inlet. Just I'm drawing some irregular things. Don't go for the size. Okay, just pay attention to what I was or what I'm talking about. Suppose this is the pipe. So initial our assumption is both gas and liquid are flowing with the same velocity. This is an at equilibrium. At any time, the feed is at its equilibrium. So when you see or when you see the two-phase criteria, whether it is a bubbly flow, chunk turbulent flow, or mist flow, or dispersed flow, or annular flow, then based on that, generally you will see liquid will be available in the bottom portion because of the density of the fluid, whereas the gas is available in the upper section of the pipe. Okay, this is the major one what we have generally used. So once this comes in, because there are some small particle of liquid which may be flowing in this zone as well, because we are assuming these are at equilibrium, so any pressure reduction will lead to any trapped gas into here, into the vapor phase, because of the change in saturation or to match the enthalpy balance in these cases. So when you have these particles, when they come inside the separators, you can see, suppose this is a circular one. My drawing is not clear at this point, so just please bear with me. So these particles which are there in this zone, they are struggling whether to fall down or whether to go high with the gas which is with they are coming into the vessel. The gas is carrying them. into separation. Okay. So when we talk about any of this liquid particle, suppose we say this is a liquid particle, there are two forces majorly acting on this liquid particle. One is the downward gravitational force, because this liquid particle have a density and then it has a weight because of the gravitational force. So liquid particle will try to fall down when it comes under the influence of gravity. In other words, in other case, if the buoyancy force or the density difference force or the gas force is capable enough to carry the liquid particle to the top, but when it is taking, it is observing a resistance. It is observing a resistance of the gas that is called as drag. So any of this particle, any liquid particle which we have to separate from the gas phase, it has a gravity force as well as a buoyancy, and there is a drag which is happening across the surface of that one. So we need to separate, or we need to understand these forces together. As I said, gravitational force will try to pull the droplet downward because of the density difference, because it has a density and that's why it has a weight, so it will try to fall down. The drag force is just nothing but the resistance which is happening across this, will try to move. When the fluid is tried to move from this surface or any of the media along with it, it will have a resistance. Like if the rain is falling from the top, like any of the clouds, while coming it may be a higher uh, diameter particle, but when it travels down, there is a resistance is happening of the air, and that's why it will break down and it will come into small droplets. Okay, that is nothing but the drag what we have, and the buoyancy force which is happening and which is trying to pull the liquid droplet to the top. So this is called as gravity settling. So here you have an buoyancy force which is carrying, or it is asking, oh, let's come together with me for the gas. But there is a resistance to the flow which is happening when it's trying to go down or upward or downward. At the same time, because the liquid particle is having a density, it is having a weight, and any weight try to fall or try to go towards the earth. That's why it has a gravity force. So to stay this fluid in the same height or in the same positions, it has to balance this force, upward, downward, and this one has to be balanced. Then only it will be stay in this position. However, being a chemical engineer or being our motto, we have to separate this fluid. So we have to increase the gravity, or we have to reduce this buoyancy and the drag force. Then only the gravity force value will be higher, and then this particle will fall down. That is called as gravity settling, and that's what we have to do. Okay, so how to define this, when this will happen, when this will happen. Okay, this will happen when your droplet reaches a terminal velocity. When this will happen, terminal velocity, if your droplet achieves terminal velocity, these forces like buoyancy forces, gravitational and drag altogether are in equilibrium, and that velocity is calculated for a sphere liquid particle by using this formula. This has been given in the GPSA, that is Gas Processing and Supply Association. This equation considers that mass of a particle. What is the mass of a particle? Its density. Generally, it is generally mass nothing but they consider diameter as well. Some 300 microns, 400 microns, 150 microns kind of thing. Generally, it is diameter of particle you can see here. And the drag is been calculated. Now, how to calculate this drag coefficient? To calculate that drag coefficients, GPSA having given a formula or the graph by which you can calculate, you can hit and you can go horizontally towards y-axis, you can get the value of drag. Or there is an equation as well which will give you the value of drag coefficient directly. So you have to have this Vt, that is nothing but the terminal velocity. Terminal velocity, that is what I was talking about, is function of drag coefficient. You can calculate the drag coefficients directly by using this graph where it is a function of Reynolds number, then the type of the particle, whether it is a sphere, disk or cylinder, and then you can use this equation directly to calculate this C into Re factor, and then again you can go back and you can calculate the drag coefficient. However, at the same time, you can use the Reynolds number by using this formula, that is nothing but the dp, that is nothing diameter of particle, terminal velocity, density. However, this is the viscosity of the continuous fluids. Okay, so this is just an introduction as well. Okay, there are some other things as well. When we talk about any separators, there is a term called gravitational settling, what we have seen, where we have a force balance. At the same times, there are other factors or other regions where the separation is happening, and that separations or that regions we generally consider, or what kind of separation we are having under the gravity settling is considered based on the Reynolds number. This is being given into GPSA formulae. These are the GPSA formulae where when there is a very low Reynolds numbers, or when the Reynolds number of the continuous phase, that is of the lighter fluid or the oil phase, Reynolds number is very less, then we use this equation to calculate the terminal velocity when the Reynolds number is less than 2. When you have a Reynolds number in the between of 2 to 500, we use intermediate law. Or when you have a Reynolds number more than 500, we use Newton's law. When you have a Reynolds number more than 500, we use this. Why we have a Newton's law for more than 500? This is because you have very high diameter particles with the lower viscosities. And that's why we use these equations to calculate the terminal velocity. However, majorly almost 99% of the separators follows this range 200 to 500, and that will give you a terminal settling velocity for any application or separators by using the intermediate law equation which is available in the GPSA. And if you wish to calculate this, what is the particular diameter or what is the maximum diameter this equation can solve, you can use this formula, and here you can use the KCR value as 0.334. Okay, uh, this is a typical chart what we have seen, uh, that is nothing but again taken out from the GPSA as well, where you have a Newton's law, intermediate law, and Stokes law. Stokes law is generally used when you have a Reynolds number less than 2, and we follow this equation, whereas only the KCR value has been changing. So that will give you the maximum diameter that can be separable by using this equation for the given properties of the fluid. Okay, this is the one method. Okay, now I'll tell you what we do with the use of VT. When you have a terminal velocity, suppose you calculate the terminal velocity for this one, then you know q is equals to velocity into area. Okay, you have to estimate this diameter, and this height. That will give you the sizing of the separators. So you know the terminal velocity what we require to maintain the separation, that is the Vt. So area is nothing but pi by 4 d square, that is the inlet diameter, and you know the gas flow rate, you know the Vt from the equations, then you can find the diameter of this one. And how to estimate the length we'll discuss in the next few things. So what we've seen is the GPSA method, whether we have to use Newton's formula or whether to have an intermediate range or Stokes law. This is the one method. Another method, what it is been there used, is called as Sidus-Brown equations, or generally it is called as K method or Sidus-Brown equation, which is nothing but the simplified form of earlier equation, where K is the terminal or empirical factor what we use for the separation sizing. Here again we are estimating the Vt, that is the terminal settling velocity, based on the difference in the liquid densities, that is the density of liquid and the density of gas divided by the density of gas as well, and this will give you the Vt directly. This is irrespective of the uh, Reynolds number what we generally use for this. Some companies, I have seen many companies which use directly this equation, that is Saunders-Brown equation, or some companies go for that GPSC method as well. Both equations will give you the more or less same results. At the same time, uh, Shell DEP uses the same equations, however, where the K is been replaced by a lambda value. And this K value go on changing, that we'll discuss. Okay, this is a typical separation uh, guidelines or chart, we can say, when to use or how to use a particular type of separators and what are its capabilities, whether the how the turn down ratio is, what are the efficiency, whether it can handle slug or whether it has a tendency of fouling, or whether how the pressure drops is. So there are various methods or separator modules what we have, that we this is taken from the GPS again, and then we'll see what are the factors we are affecting on this separator sizing. As we discussed the flow rate, when you have a very high gas flow rate, we generally go for vertical, and if you have very high liquid, then it will go for the horizontal one. Separation quality is again the critical one. Like as I said, if you require very pure or the clear gas, we generally go for the vertical. Surge and retention time, again the major one, which defines generally the orientation of the fluid. Degassing, again how much is the gas trapped with the liquid. Plot space, uh, this is one critical one. Height for the transportation and building, like whether you have to design a 40-meter height or 40-meter length vessel, then you have to think for sizing again. So there are some various factors that has been there. When we talk about the horizontal gas and liquid separators, these are the few things, and this is the various criteria what it has been defined in GPSA. These are gives you basic idea about this. When you go for any client design or any particular guidelines like Shell DEP or ExxonMobil standards or ADNOC standards, then they have other requirements as well. But those has been defined or derived from the basics basis reference of GPSA and API 12J. Okay, now before jumping to uh, the internals of any separators, we'll try to find the how to find this height. So let's go back and redraw this. Okay. Okay. So this is the tan line, and this is the tan line. Okay. So being a process engineer, and if you have to size any two-phase separators, you have to estimate two major things. One is the what would be the diameter of the vessel, and what would be the length or height of the vessel. So we have seen how to estimate the diameter. You have to estimate the terminal velocity, and then by using the equation, that is q is equals to terminal velocity into area, you can estimate the diameter of the vessel. But when we talk about how to estimate this height, then you know uh, every vessel is being provided to provide a residence time to the liquid. Okay, so that to ease the separation or to separate any trapped gas in the liquid. So there are some basic rules or basic things what we have, or liquid levels generally we call it as. The lower one is called as low liquid level or low liquid level, that is LLL. Then there is called as low liquid level. Then there is a high liquid level, and then above that there is high liquid level. Some companies call it as Z as well, LZH, or directly LLL. Some companies called this as LAH, HAL, LAL. It is LH. It is LAL. Then this is called as LZH. This is LZL. That is nothing but to trip. There is also a normal liquid level in between the high liquid level and the low liquid level. So how to define this level? It has some rules. Okay. So generally, this lower one, low liquid level, where your outlet wall needs to be closed or the pump needs to be tripped. Suppose you have a shutdown wall here, then it is been given a condition that it will trip this wall or it will trip the pump. So this low liquid level is generally 150 to 200 mm above the tan line. Above the tan line. Okay, this is the major one. Then low liquid level, I will use this color. Low liquid level to the low liquid level is minimum 150 mm or 1 minute time. 1 minute residence time of a liquid. So what is the volume it is coming in 1 minute based on the separation liquid capacity? This level has been estimated, and then you have to select the highest among these. This high liquid level to low liquid level, this is being defined as a minimum 3 mm. So people will define this 3 mm into high liquid level to this NLL as a 1.5 minute, and NLL to low liquid level, that is LAH or LAL, it is, that is 1.5 minute. So what we do, we assume some liquid levels, we find the volume, and we know the volumetric flow rate. So the volume by volumetric flow rate will give you the time. Okay, so you have to see how much is the resident time between these two stages. And for high liquid level, where it rings the alarm, this rings the alarm, this rings the alarm, this trips the bottom, high level trips the feed. This is, so this part, that is high liquid level to high is again the 1 minute, or generally 150 to 200 mm. Okay. So this is the typical one. Suppose let me see if I can draw one more point. So we know the timeline is 111. Okay, 1311 means on the type of applications, service, and flow rate, whether it is feeding to your reactor, whether it is feeding to compressors or feeding to plant, whether it is feeding to fire heater, these requirements go on changing. These type requirements go on changing. So you have to be very cautious, and this has been defined in the GPSA. So you know 1 plus 3 is 4, 5, 6. So you know 6 minutes residence time you require from high liquid level to low liquid level, where your fluid needs this much of residence time, total residence time in vessel. So you can 6 minutes multiplied by what is the flow rate, Q divided by 60. So you will come to know about the volume, how much volume you have to store between this liquid level to this liquid level. Plus this has a minimum 200, that we'll see. So this volume, so you know the diameter based on the Vt, that is we have estimated the terminal velocity. The same diameter we are using. So it is nothing but pi by 4 d square into the h of a liquid. Just let me expand this. This is the h of a liquid. H of a liquid means, let me use this. So this much section, this much section you have to fill with, or how much is the volume you have to store. 1311, that is 1, this is 3 minute, 1 and 1. So you know how much time is the residence time you require, you know the volumetric flow rate, then based on that you can estimate the liquid velocity, liquid height. This is the liquid height you require for the separator. When you see, let me open one more. So now you will see how it is affecting. This is the tan line, this is the tan line, this is the tan line. So this is your liquid level you require, that is H of a liquid. Now there is a inlet nozzle at this point. This is the inlet nozzle. So from high liquid level to the bottom of this inlet nozzle, high liquid level where your plant is getting tripped or inlet feed is getting tripped, there needs to be a minimum 150 mm or 200 mm gap between the bottom part of the inlet nozzle to the high liquid level. Then there is this nozzle height, that is the nozzle height is also coming. Then you require minimum this upper section as 600 or 900 mm when you are not using any external device to enhance the separation. Suppose there is no any inlet, no any device is present in your system. It's just a simple cylinder with the inlet device. Then inlet nozzle, what we'll call. Then you require minimum 600 or 900 mm based on the guidelines. Some company uses 600 or generally it is 900. Then this, suppose we are using 900. So tan line to this is 900. Then this height, say you are having a 4-inch nozzle, so this is 100 mm. Then this portion, that is the bottom portion of inlet nozzle to the high liquid is 150. Based on the total residence times, you have estimated the maximum height to the tan line, that is HL. So your total length is nothing but 900 plus inlet nozzle size, that is 100 at this moment I'm considering, plus 150, that is the difference between the high liquid level and the inlet device bottom part, plus total liquid height, suppose I'm just assuming as 600 minimum, plus any additional margin you wish to consider. So 900, this is total 1000, 16, 1750. This is way you estimate the total height of a vessel, whereas diameter, that is the ID, is estimated using the VT, that is the terminal velocity. You got it, or shall we define this again? Am I audible? Can anyone define it? Can anyone open and talk, please? Open your mic.
Yes, sir.
Yeah, sir. Yeah, tell me. Any doubt in this one?
No doubt, sir.
Okay. So what we are doing, we are estimating this ID by using the terminal velocity. However, residence time, we are using the residence time to estimate this high liquid level from the tan line. Then we are know this minimum distance what we require between the inlet nozzle bottom part to the high liquid level, that is this distance. Then the nozzle, obviously nozzle is part of height, so that will be added. Then some company, if you have an demister pad or others, they consider 600 mm, or if it is not there, they consider 900 mm, or generally some companies directly consider 600 mm irrespective of the inlet device, the separating device is available or not. So summing up all this will give you the total length of a separator. Clear? Now we'll jump it back to the next one, where we consider the various part of a separator. So now we found out how to estimate the height and diameter. So when we talk about the various part of any separator, there are majorly 3-4 parts. One is the nozzle, where majorly separation happening because it is open, directly opening to the higher area than the inlet one. There is a gravity section. Gravity section is nothing but this region, where completely a gravitational force is having higher value over the particle molecules or the separating molecules or the droplet. So the separation is happening because of the gravity. There are some mist eliminators. Mist eliminator means we are using this part, the upper part or the vapor space, we are putting some mist eliminators. Like these are nest of a wires through which gas has to pass. And when it passes through the nest of a gas over this nest, it strikes out to the surfaces of the wire or the material by which or from which this nest has been created. So at every striking position, the shear or the surface tension of a liquid or the density of carried liquid comes together, and that will try to coalesce and fall down. That's how we are getting the separation very handy. That is called as mist eliminator devices. Any downcomer that will see down the lines, outlet nozzles and the liquid level controls. That are the typical parts of any separator. Yeah, this is what we discuss about what and all information we require, like whether it is having offshore, onshore, or gas plant, what type of separating item or applications what we have, whether it is KO drum, inlet separators, compressor inlet separators, or some kind of solid removal, whether there is any space limitation. Suppose you are doing any brownfield project and you found that there is a typical no space available, you have to dismantle the existing one and you have to fit the new one to have a higher efficiency or higher separation capacity. So space limitation is one major criteria. The sizing parameters, again based on the what type of service you are handling, and other parameters what we have seen. Okay, this is what we have talked about, the inlet devices. Inlet device means the device which is placed at the inlet nozzle, which allows or which help to ease the separation. Okay, ease of separation. These are the devices been there to allow or to help the separation. And there are various inlet devices. That is, no inlet device means there is nothing is available. Some kind of half open pipe or deflector plates has been used, or we generally use suppentator. Suppentator is the one which has been designed, developed by the Shell company, and this is a proprietary method they use. This inlet device uses the momentum separation criteria. When the fluid strikes to any surface, it changes its direction, at the same time it loses its momentum, and that's how it helps to ease the separation. Okay, uh, when we go for mesh size or mesh pad, generally call it as mesh pad, is nothing but there is in this region, what I guess I have drawn it. This is the mesh pad design. we generally don't do any mesh pad sizing. This has been provided by the vendor only. And even though whatever we design, we majorly trust, or we follow the design defined by the vendor only. There are various vendors in the market who do provide this suppentator or mesh eliminators or vent pack and other things as well. Okay, so this has been used when you have to have a higher separation efficiency requirement and very less low pressure drop, but pressure drop is more when compared to there is no any mist eliminator available in the systems. When the system is more vapor dominant, means when there is very high comparable volumes of the vapor available in the system, and because of the high volumetric flow rates of the vapor, the carryover may be higher, or the flow velocity of the vapors is very high. So there is a chances that, because rather than separation, liquid droplets may be carry over to the next section, or without any separation to the next level of the equipment. So there are different mesh types, like majorly metal, plastic, composite, and compound. But majorly these are made up of wire, and generally it is stainless steel wire. Venpack. Venpack. Let me. Okay, let me draw it here only. Okay, Venpack is nothing but some plates are arranged in this fashion. There are some plates which are arranged in this fashion, and those are bolted. These are placed in this region only. If it is vertical, your gas will come, it will strike, it will change its direction, it will change its direction and strike continuously while going upward. And when it strikes, as I said, it changes its direction and loses momentum. So the liquid particle will try to stick to the surface, and this will form a layer, and this will trickle down, and they will directly fall from this. When you have an horizontal one, this vent pack is generally like this one. So whenever the fluid comes in, suppose this is one is coming, when it hits here, the liquid particle will accumulate in this zone, and it will form a bubble or very high drop, and they will form here. So there is some channel kind of arrangement is provided at this bottom part that will all together collect in one side, and then this will be separated in this zone. So this is called as vent pack. Uh, this is just nothing but what are its considerations, as well as what are the reasons or advantages, what we can say. The same is been there in the GPC equations. Okay, so vent pack, as I said, vent pack can be arranged where the flow is in vertical directions. What we have seen, this the flow is happening in the vertical direction. You can use the vent pack in vertical directions, or you can use the vent pack in horizontal directions. Like there is a flow is happening like this, and that will flow along this side, and the gases will go upward, whereas the condensed liquid will fall down through this pipe connection. This pipe connection, generally as per the shell, it is minimum 2-inch requirement. However, this is being sized by using the fraud number, and generally they go for zero point 0.2 to 0.3. But generally I have never seen any of the vendor which is considering the sizing of this one using this fraud, and generally they follow minimum 2-inch or 3-inch as their company standards. Or you can see again the horizontal one, where gas molecules are flowing into horizontal sections. But whenever we have any separating device available in the systems, there are three main zones. The one zone which is wherein the separation is happening because of the gravity. The next one is because of the forced media or external media available in the separator, which is there to enhance the separation. This is in horizontal direction. This is again into horizontal. In this one, the flow is happening into vertical direction. No inlet device or no internals. No internal means there is nothing in this one. Just simply like this. There is a hollow cylinder with inlet, outlet for vapor, and outlet for liquid. That's it. No any separation or enhancing media available in the separator. And it has its own advantages, like it has a very low pressure drop because there is no pressure drop available, like any media or any part available in the vessel which allows or asks for higher pressure drop requirement. Sometimes it is not that much sensitive to the fouling. Fouling in the sense some kind of foreign materials or the rusting of iron piping iron material, it generally comes back, and that will stuck into the this vents or mesh pad, and this is the separation efficiency what we have seen. When we talk about this common generally liquids horizontal liquid separators, we can use the mesh pad or the vent pack in the same as well. At the same time, when we talk about the horizontal separators, there are some external mediums what we use. I'll just tell you. Suppose this is the inlet nozzle, then there is a calming baffle which is having holes in this one, which has some vent packs in between, which has a mist eliminator here. This is the gas outlet nozzle. This is the overflow weir. This is the heavy liquid out, and this is the light liquid out. So this we can use. The calming baffle is there to regularize the movement of the liquid and to lower down the fluctuations so that we can have quick separation in this. So when we have a three-phase separators and when you have the vent pack is arranged like this, the fluid is flowing in between this region, between this section, and while its movement, it again touching to the surface, changing its direction, and small particles of the light oil or the light density fluid coalesce together, and when it comes back, they will directly try to move upward, and the heavier particle will try to go downward. Same time, the Smith eliminator is helping us to drop or to allow the separation of any of the small particles which has been carried out by the gaseous fluid or the gaseous part. And this liquid level is like this, only the lighter fluid is flowing over this, and there are some vortex breaker, no doubt here the vortex breaker has been provided. Okay, so this is the typically what we have as a horizontal separators. Here what we have, this is called as primary separation zone, this is called as gravity separation zone, and this is secondary separation zone where we have this all materials in there. This is the typical one again. Let me see. This is the typical again. This is giving you an idea about what we call it as a typical idea about its advantages, disadvantages, how much is the retention time, what are the applications where we can use this, or this is the areas where we generally prefer to have a three-phase separator. That is majorly a horizontal separators compared to the other vertical medium sector. Okay, now when we are talking about this separator sizing, there is again a major part. Being a process engineer, what we have to do, we have to estimate this part. diameter and the length or the height of the vessel. However, at the same time, we have to estimate the nozzle sizes. What would be the nozzle sizes of inlet, nozzle sizes of the outlet, gas outlet, and this liquid outlet. So we have to use, or we have to find these nozzle sizes as well. And there are some other methods or other inlet devices we have. That is what I said, no inlet device. Like there is a no inlet device means directly the nozzle is connected to the vessel without any additional part attached to it. When you say the next one, I will just draw it here, 2 3 parts. The inlet device, no inlet device, only nozzle. The next one, the inlet device with half open pipe. Half open pipe means, or the deflector plate. Then there is a suppentator. Suppentator is like this. It is connected here directly. It is up to here. This point is okay. So this is because of the rho v square values. That is the momentum. When you have a no inlet device, we can consider 1400 kg per meter second square as a momentum. You don't have to cross this value. So you know rho v square value as 1400. So you know this velocity how to calculate. You know the size, the assumed size of this nozzle. So you can calculate the Q by A, that is the rho v square value. This V, this V is the velocity. However, this rho is the rho of a mixture. It's not the density of a gas or density of liquid. It's the combined density of this inlet or incoming feed. So you can assume the 4-inch and you can calculate this velocity by Q is equals to V into A for the nozzle, area of a nozzle. So you can assume the diameter, you know the area, you know the Q, that is total volumetric flow rate it is coming, or by using the mass equation, that is mass flow rate is nothing but the rho into Q, that is nothing but the rho, that is the density, V into the area of a nozzle, and then you can calculate this velocity. If you know this velocity, you can use this velocity here and you can check what is the momentum through this nozzle. So if you are thinking that you don't have to use any inlet device, then maximum value you can go for is 1400 kg per meter square. If your liquid content is very high and if you want quick separation, then you can use half open pipe. Half open pipe. And that has a rho v square value limitation of 2100. This I am telling you about from the Shell DEP. When you are using the Shell suppentator, you can use 8000 or more than that. 8000 or more than that. However, the same equation follows here for the gas, and you can use 4500 rho v square, or generally 3750 based on the company guideline again, generally 37 to 400, 4000. You can use to size the diameter of this nozzle, like how to size or what are the design or the deciding factor for this is the rho v square values. So these are the typical rho v square values we consider to size the nozzle sizes of a vessel. Now this is typically for the inlet and the outlet of a gas nozzle. When we talk about this liquid outlet, generally it is being sized for 1 meter per second velocity. Some company I have seen they use 2 meter per second, but generally this is not recommended. Generally, it is being sized for 1 meter per second velocity of a liquid being utilized or being used to calculate the diameter of this nozzle size. Okay. Okay. These are the typical advantages or effectiveness or the benefits what we get when we are using the different devices, or when you have very high uh, volumetric flow rate of gases, then we use the cyclone type inlet devices as well, that we generally don't do any sizing for that, but those are there. Okay, so this is the typical length considerations. So when you have horizontal separators, let me open this. Suppose this is an horizontal separator and your gas is coming into this side, two-phase fluid or three-phase fluid. Being this is directly opening to the higher area vessel or higher area pipe, like suppose this has a pipe, then because of the change in diameter or change in the area, you know, the Bernoulli's equation tries to match the energy. So here the pressure energy what you have, it has been converted into the vapor head, and that's how this will try to flow in this region. But as it comes into this region, there are three phases. So liquid will try to go down, liquid will try to go down, liquid will try to go down, go down, liquid go down, where the gas will continue to rise, continue to rise. Okay, so this length, the length from tan line to the tan line, it considers this effect into consideration, and that will give you what are the maximum velocity you can consider, like what we are considering as a VT, terminal velocity, and it considers the effect of a length in the equations. Whereas in case of vertical separator, there is no parameter which is in there or which is just considering the effect of a length to calculate the velocity. What's happened if you are at this region, your velocity may be different. This region, some of the fluid has been fall down, so the fluid flowing in forward direction has been less as compared to this side. Even if you go further, the volumetric flow rate of the fluid available to flow in the forward direction is lesser in compared to the earlier ones. That's why to integrate it over the length, you have to have a length as a parameter. At the same time, you have some other parameters as well. When your operating pressure is going high, when your operating pressure is going high than atmospheric, you have to multiply the K values by this factor. Okay, you might to multiply the VT or the max or value by this vector. There are some other values or typical values being there given for the K value. Earlier one for the Vmax or the VTs, whereas this one are typically the K values. Saunders-Brown equation, K values. Based on what type of arrangement you have, what type of arrangement you have, what kind of inlet device you are using or separating device you are using, whether vertical flow to the mesh, horizontal flow to the mesh, whether you are using any vent pack, vertical or horizontal. Combination of this one will tell you there are some. Let me clear this. So I will try to tell you one typical case what I have seen. So there is a Schupentator as an inlet device. Then we have a vent pack. Then we have mist eliminator, or sometimes you have this cyclone separators too. Generally, shell is called as Schuppenritter, mistmat, and SMSs, Schuppenritter, mistmat, and what it is, the name I forgot here. But generally, they define this type of arrangement. When you have more than one enhancing materials available in separator, then those are defined using their names like this. The first one is generally for the inlet devices. The middle one is for the helping media like a WAN pack or mesh pad. On this is cyclone separators or anything else what you have. So generally, to reduce the diameters, or generally not measuring the diameters but the height of the vessels or height of the system, you will use, or you have to use, multiple devices into your separators, and that's how you can come to know the, or you can help to reduce the height of a vessels. This is the same what we use in these cases. uh, that's what we have seen, that is how to control the liquid level, low liquid level. Then NLL, and that is nothing but there is a search. Suppose in case of whether your feed is coming from the own platform, whether the feed is coming from the own platform but with the lift gas or the injection gas, or whether the feed is coming from the adjacent platform, you have some different uh, flow multipliers you have to consider for the incoming feed. Or sometimes there's kind of slug is coming, high volume liquids are suddenly falling into your separators, that may disturb or creates a problem for the separation, quick separation. So you have to define, or you have to design your separator to accommodate that volume without affecting the separation capacity or separation efficiency. So that extra slug volume is being allocated between the high level alarm and normal liquid level, high level alarm and normal liquid level. And this is what we are talking about, low liquid level, where the trip is happening, or the tripping of a down outlet shutdown wall or pump is happening. Low liquid level, low liquid level means it is giving an alarm to the operator. Normal liquid, where we are operating in a normal day out. High liquid level, it is the liquid level above the normal one, and that is giving you an alarm to the operator that something is different, or some liquid is going high, whether it may be because of the pump trip or outlet node liquid control wall has been closed or the down wall has been closed. Even though if liquid level rises high, at high liquid, it creates the tripping, or it creates the closing of the inlet device or inlet control walls. And every difference between these nozzles or these liquid levels have the design requirements, whether it is a time one and another one is the minimum gap. If we do not consider the minimum gap, suppose say there is a 100 or 150 gap between the high liquid level to high liquid level, and if we consider minimum 70, so what happens if we puncture, and if we actually try to measure this, then it is quite difficult for the level measuring element to correctly measure those. That's why the minimum is minimum 100 to maximum 200 gap is being provided between the two liquid levels in the plant. And this is generally we ask in case of interviews. When we are interviewing any senior or any mid-level engineer, we ask why we have a difference in level settings. We can consider directly 50 gap between these two. So you can imagine if you have a 50 gap, so any furious action can lead to alarm or tripping actions. So to avoid this, we generally provide a gap based on the time, or based on the leveling measures equipment to correctly measure those. Yes, this is what I was talking about. This is the minimum retention time or control time, generally it is called as, given by the API based on the type of device or application of a device where you are using this, where you are using this. And this is the general guideline you have to use. You can divide this time limits as per your own convenience or based on the company guidelines for whom you are preparing the engineering documents, or when you are doing any separator sizing and you do not have any criteria, you can follow the GPSA equations or GPSA time limits given for that particular application. Even if you are doing any retrofitting, you have to ask for this time limits what they have considered initially while sizing the separator. That will give you an idea about the requirements. So this is just what about we have for the separator sizings. So do you have any questions in this? So we'll quickly jump back to the separator Excel sheets. Unfortunately, I have taken this from the internet, and this is what we have. We'll go into this, but before that, do you have any questions for this one? What we have discussed till time?
No.
Anyone? Let's
No, sir.
go back. Let's go to the separator sizing. What we have generally seen. Each company, whether it's engineering companies majorly or the vendors, generally have their own programs, computer programs, or the Excel sheets developed internally based on the Shell DP guidelines or ExxonMobil guidelines or GPSC equations or generally API 12J equations. Uh, they have generally Excel sheets, whereas the final design is being there from the vendor, whether it may be a Schlumberger, whether it may be a Technip FMC or any other local vendor too. So what we seen, this is the same criteria what we have used. So generally any sizing sheet look like this. Based on the company it may change a little bit, but this is the same. You have to feed this yellow highlighted cells, that is the vapor flow rate, its density, this is the volumetric flow rate, and all other drop down are also there. This will help to calculate the volumetric flow rate of the fluid, liquid flow rate, and its density. These all four parameters, the flow rate and density of each phase, will help us to calculate the combined mixture density, which is required for the ρ square value considerations, or to calculate the nozzle sizes. What we have seen, when you are using no inlet device, you have to consider 1400. If you are considering half open pipe, you have to consider 2100 kg per meter second square. If you are using supinator and you wish to reduce the size, you can have to have 8000 or more than that. But just be cautious that when you have 400 or more than that ID, then only you can use supinator. It's else it is quite difficult to manage the supinator in a smaller sizes. Okay, so this is the operating pressure. Special requirement is generally whether it is any the location of the vessel. The K value, Saunders Brown equation, we generally you can calculate this or you can consider this, or you can put your value, say 0.75. So you can see the change in this one. Suppose if I remove 0.75, you can see ID here as 800 but now I remove this, so you can see, so higher the K value, lower is the diameter. Okay, higher the K value, lower is the diameter. We ask this question to engineers when they come for interview. So what would be the impact of K values on the diameter of a vessel? Okay, so this is a quick example what I wish to show to you. Slug capacity. As I said, slug capacity is any sudden high volume fluid, liquid fluid is coming or falling into the vessel. Then you have to accommodate this. So let's see, you consider this between NLL to HLL. Slug capacity we have defined, hold up volume, that is the retention time you have to define. Generally, in my company or wherever I have worked, we generally don't define this as a directly hold up time, but we generally define the time as NLL to HLL, HLL to NLL, then, or what I have defined. Let's see it here. So we define HLL to high liquid level, then high liquid level to NLL, NLL to low liquid level, low liquid level to low liquid level. We define the minimum time requirement or minimum the distance requirement, and based on that, program will define the total height we require to accommodate this all things. Rho v square. So feed inlet device rho v square. Suppose if I have to consider no inlet device, so I will define it 1400. Then you can see the nozzle diameter has been changed. Suppose if I consider 8000, so the nozzle diameter has gone down. If I consider the limit of 2100, the requirement has gone high. Okay, now you can see the changes is happening, and that is because of the rho v square what we are getting. Outlet nozzle, we generally have 4500. Liquid nozzle, you can say 1 meter per second. So your actual size is not changing because it might be giving you more conservative value. Generally, in this sheet, it has been given L by D, and then it is calculating the other parameters. However, I'll just show you one more sheet. Here you can see, let me remove, or let me have this as well. You can see my screen, right? Okay. So what we used to do, we generally define these parameters, yellow parameters. In actual, when we are doing any sizing, we define this typical inlet line. I just consider say 6 inch. Then I will come to know what is the uh, velocity sizing you are giving. At the same time, it will give you rho square values as well based on these sizes. Same times, I will calculate or I will force some values. So directly I will give values and program will tell me what are the minimum sizes I need to have. Okay. So this is how we do kind of a rating arrangement. We generally don't go for sizing or defining all these value. We generally say this is the minimum. Say low liquid level I'm considering 200 mm. So what would be the NLL height? What is the minimum volumetric or volumetric minutes setting time we are getting? So this is what we get, and there are some checklist what we have. So generally we do this kind of sizing. Let me see, just a minute. I'm trying to get one more. Okay, this is what we have. No, I'm actually not getting that sheet, else I would have shown it. Okay, so we use generally this kind of sheets to size the separators, and that will give you various calculations. Generally, we feed these value in this part, and the results has been generated and been checked with the standards, and then the results has been defined like this. Like remarks has been checked whether it is okay, not okay. You have to increase the length, decrease the diameter, or change the nozzle diameter. This kind of errors the program gives, Excel program generally give, and then we develop the data sheet accordingly. So do you have any questions in this? So do you have any questions for this? We can now discuss about if you have any queries.
Thank you very much. Please, I have a question.
Yeah. We'll be happy to help you.
All right. Please, I want you to throw more light on the issue of the relationship between the K value, increase in K value and diameter you mentioned earlier.
Okay.
Thank you.
Okay, let me just reshare my screen. Okay, let me take you to the equation of K. Yeah, here you can see. So your equation is V terminal velocity is equals to K square root of rho of liquid minus rho of gas divided by rho of gas as well. So that means suppose if we have this as a constant, this is not changing. So your velocity in this is directly proportional to K. But if you go back, your velocity is inversely proportional to the area. So if this goes high, your Vt is going high. However, your area, that is nothing but the diameter of the vessel, will come down. Your velocity is directly proportional to the K. However, your velocity is inversely proportional to the area. So any increment in velocity will come down or bring down your area to the downward side, and that's how your diameter of the vessel will go down. Is this clear?
Yes. Thank you very much. Very clear now. Thank you.
Yeah, thank you.
Sir, what is that Vmax relations which you shown before
Yeah.
showing sizing calculation?
Yeah, Vmax is nothing but the term what we use for the horizontal separators. Let me go back here. Generally, we have Vt, that is terminal velocity function in case of verticals. But when you go for horizontal, here you can see, which considers the effect of a length. As I said, in case of this one, when the fluid enters in this region, okay, some particles are settling in this side. So any region, suppose this is the region you are considering, then the mass flow rate or volumetric flow rate in this region is not same as that of this region, because some particles have been settled because of the gravity. So your Q by A, that is the flow rate over the area, your area is not changing. Your area is not changing. The diameter and the lengths are not changing. But your Q is changing over the length. That's why you have the function called as L in between. That's why it is called as Vmax. Clear?
Means for horizontal we have to find Vmax because volume flow rate is changing.
Yes.
So sir, you mentioned the let's suppose 6 minutes is standard for hold up time, okay, which is multiplied by volumetric flow rate, so
Correct.
which gives volume,
Yes.
and volume is equal to pi by 4 d square h, where d is the diameter of separator.
Yes.
So only H is unknown. So whatever H we find out, it is the liquid level only or total height.
No, no, we calculate the liquid height based on the liquid flow rate only. So whatever the liquid, whether it is separated in this zone, whether it is separated this zone, or this zone, it is accumulated over this length only, or in this region only. So you are estimating this. Let me use different color. So your liquid level in this height. Suppose we take an example of 1311. That is high liquid level. That is alarm to the trip 1 minute. Alarm to the low level alarm is again 1 minute, 3 minutes, and then suppose if you have suppose you have again 1 minute is the gap between the low liquid level and low liquid level, and this is the bottom one. So this all liquid are arranged in this section only for horizontal separators. In case of verticals, you can see this. These are being defined in this zone completely. So anyhow, in this case, what happened over the diameter, whether it is separating in this zone, because there is no height which is enabling or creating more separation. There is only a diameter in case of vertical. But when you talk about the horizontal, this is the length that plays the role. That's why this L comes into picture in these cases. So you can use the inlet flow rate.
No.
So whether it condenses here or here or here, this is falling down and calculating or giving a value or playing a part in the liquid height or liquid level considerations calculations. So it doesn't matter. You
So
consider
my
the
question
liquid.
is how to find liquid height, means whatever liquid height.
Yeah, liquid level heights are based on the two criterias. One is the time limit and one is the gap between the two intervals. Generally, as per this GPSA, they have given some minimum time limits based on the service or application where your drum or vessel has been used. Same way, you can use the minimum gap between the level intervals, low liquid level and low liquid level. This low liquid level means this is gives you an alarm. Here you have alarm.
So once I define total minute, let's suppose 10 minutes somehow by thumb rule. So now how I can proceed for finding height of liquid?
That's what I'm saying. Suppose let me go back here. Okay. Now say suppose if you are considering 10 minutes. Okay. Suppose I'll take an example of vertical first. Suppose you are having 10 minutes. It's 10 minutes is not like between tripping to the trip. So you will be generally having normal liquid level, that is called as NLL. There is a LAH, that is called as high level alarm. LAHH, that is trip is happening. Same way, that is LAL, and there is LALL, low liquid, or LZH generally called as. Here there is a tripping action. Same way, here there is a trip. This is giving you alarms. Okay. Now, if you see the control surge or the control time between this generally, or the retention time generally, let's forget about anything. Now you are saying you have a 10 minutes. So based on your plant location or accessibility of the vessel or reliability on the instruments and qualified operators who can take quick action. We generally define these 10 minutes such a way that alarm to trip is 1 minute, high level alarm to low level alarm generally say 4 minutes or 6 minutes. This is again 2 minutes, so it is 9 and 1. So you can define these values. So this is based on the time. Suppose this is the one criteria. However, if you are deciding, suppose if you have wish to measure this value, then you have to puncture these nozzles in the system. Then only you can measure this value. So measuring elements also need some clearances, or the nozzle also some need clearances. That's why what we do, we keep, suppose there is a tan line, so minimum 1 minute gap or 150 mm, whichever is maximum. Okay, so what we do, we generally consider, say this is the bottom tan line as 0, so I will put my LALL. This is minimum required as 150 mm or 200 mm minimum, and by time I required this as a minimum 1 minute. So I know how much volume I can give. Suppose if I put this as a 150 mm above this, so 1 minute I know how much is the Q by 60. This is not the case. You know how much is the volume you have to store between this nozzle. Same way, suppose you have to put LAL, that is the alarm from the bottom. Minimum requirement or the gap required is 150 mm, but you're allowing 5-minute gap. Means from alarm to the trip you have to allow 5 minutes. So you can calculate how much volume you have to store between these two nozzles, between these two levels. So 5 minutes divided by volumetric flow rate of liquid divided by 60, that is the conversion of meter cube per hour to meter cube per minute. So this much amount of volume you have to store between these two. By 150 mm, this is the minimum requirement. But if you look at the 5-minute time requirement, this much amount of volume you have to store between the two levels. So you come to know that you have to store around 8 meter cube. Okay, so you know the diameter you have estimated from the equations, that is the terminal velocity. So you know the formula, that is pi by 4 d square into h. Okay, this is the volume. So you know this 8 meter cube you have to store based on the 5 minute. You know the diameter you have estimated from the Vt, that is the terminal velocity equations. You know the pi by 4 value. So you come to know that h requirement for this is 330 mm to have a time limit of low liquid alarm to the low trip. To have a 5-minute gap, you need a liquid level of 330 mm gap you require by based on the time. But as per guidelines, minimum you have to keep 150. So you have to use the highest among these two, 150, that is the what minimum required, and 330 is the height you have to require, so that your alarm and trip have a 5-minute difference. So you will consider 330. So lower one is 150, then the next level from here it is 330, or you consider 350. Now again from here you come here up to this alarm point. Now you want your NLL to be 2 minutes away from the alarm point, or minimum 100 mm. Using the same method, you can calculate what is the minimum distance it is required for 2 minutes, or 100 mm is the minimum. Which is the maximum among these two, you can consider that value and you can sum up together. This is how we estimate the liquid levels, different liquid levels. Is this clear?
Yes, yes, sir.
Sir, what
Same
should
for
be the
horizontal.
sir? Yeah, what should be the orientation when we choose flash drum at working under reduced pressure or vacuum?
Yeah, vacuum, generally vacuum we consider the vertical vessels only. Generally there is based on again the what kind of liquid you are getting, whether if you have a very high volumetric liquid, suppose you have a vacuum columns, so you would be having a vacuum distillation column, next to that there is a condenser followed by a separator, like a three-phase separator or a reflux drum we generally call it as. So in that cases your vent is connected, a vent nozzle. Let me draw this, see if I can draw here. Okay, suppose you are having let me use this. Suppose this is the distillation column, there is a air cooler followed by separate cooler, water cooler, then you are having kind of this application, and this is connected to your vacuum system. Okay, so generally based on the liquid or the applications, this is generally horizontal only. But if there is a very less volume fluids, because if you go inside these systems, you will observe vertical separators here because less liquid volumes are flowing here. That's why these are verticals. But if you refer to the application and the liquid content, and even though those are applicable or working under vacuum, you will observe that this will be horizontal ones.
Yeah, what if the inlet of the separator is coming from a falling film evaporator and the flash drum is connected with the vacuum line? So what should be the considerations in this case?
Can you come again? If you have a falling film evaporator,
Yeah, falling film evaporator. The falling film, the separator is mount. The falling film evaporator is mounted upon the separator.
correct.
So in this case, how much should be the what should be the orientation and the liquid level, gas velocity?
No, gas velocity, we do not consider gas velocities ever.
Okay.
We do not consider gas velocities. I never talked about gas velocities. It's all about the terminal velocities, the liquid dropping velocities, or the K values. If you are using Siders-Brown equation, you have to use the K value. If you are using the GPSC equations, you have to consider VT values. When you have a falling film evaporator, generally evaporator means a higher percentage of liquid is being converted into the vapor forms. So your liquid level at the inlet of this is minimum. That's why it should be vertical separator only.
So in this condition also we should calculate low liquid level and everything.
Obviously, unless and until, I'll tell you some examples. Okay, if you have seen air compressors in your plant, so that is having an cooler and air compressor, I'm talking about air, then this is the separator, and this is generally have a manual valve. Or even though if this air is coming from OSBL, outside battery limit, to inside battery limit, generally companies provide a separator at this point with a shutdown valve if a company like ADNOC is there, then they provide this kind of arrangement. If high liquid is there, then they provide open this wall. Low liquid is reached, close this wall. Or Indian companies provide manual wall and they put SOP. Once in a shift, you have to open and drain any of the condensed liquid. This is nothing but the moisture. So if it is this kind of intermittent application or very low liquid content in the gas, then you don't have to go for control arrangement. But if your system is continuously operating and you need a monitoring of the vessel, then obviously you have to provide alarms, trips, then pressure gauge requirements, safety valves, then what we have, wear and all other requirements.
Sir, in this condition, the liquid level is going to be very less compared to the vapor rate. So,
Yes.
is that necessary to do the liquid level calculations?
Yes, obviously, even though generally, if this is the pure gas, 100% gas, then also you have to consider 2 to 4% when you are comparing the what we call it as total mass. Suppose your 100 kg per hour is the mass coming, so you have to consider 2 kg or 4 kg per hour as the liquid flow rate coming to your vessel. If that is after the third stage of compressor and you are very much pretty confident that there is no chance to have a condensation in this zone, then you can omit that. But generally, whenever you have any ISBL or OSBL coming, you need to have a separator at the inlet of any phase or any fluid coming across the borders with blocking mechanism and all. Whether it might be the feed, which is the product of earlier plant, or whether it is instrument air, or if you are sending something, then that other plant would be having a separator, or generally it is a practice to have a separator to separate the any condensed fluid over the length.
Yeah, thank you, sir.
Yeah, thank you.
So one
The
is from
same
my side
consider
actually.
for horizontal.
Sorry, I'm unable to hear you clearly. Yeah,
Same
Mr. Rahul
repeat.
saying, or yeah, Akash Soni. Yes, sorry. Yeah, Akash Soni, you are.
Sir, whatever you taught me before this question, like the calculation of height of the liquid. Okay, so same thing we repeat for horizontal, right?
Sorry, can you come again, please?
Whatever you taught to calculate height of the liquid for vertical separator.
Yes.
Okay. So same I have to repeat for horizontal, like I have to divide high liquid level and calculate the horizontal volume, horizontal separator volume formula.
Yeah, absolutely, correct.
Okay.
Terminology, calculations,
one is from
everything remains the same.
Actually, in the vertical separator, as we have considered regarding the height, diameter will be come from the the terminal velocity concept, and
Yes.
the height as we consider based on the safety factors and operators reaction time that we considered while considering the alarms and the trips. In most often the cases, please correct me if I'm not wrong. Most of the cases, the response time of the operators used to be taken at 1 minute, or the length that we are considering between the normal liquid level and the low liquid level and the low liquid level are usually taken as same as for almost all the cases. I think. And what we have considered like five for the 5 minute buffer. This case is not usually I think taken in the industry. So conclusively, I want to know that in any case, if we are going with these level standards, so ultimately the what is the contribution of the flow rate to deciding the height? One is
Yes.
that, and another one is that I think that in any cases the height of the column, height of the separator used to be remain constant in any application in this way or in any flow. I
Yes,
think.
yes. Height. Once we design the equipment, suppose you are running. Suppose take an example of offshore platform. So in the early stages, your oil will be very high, or the liquid flow rates are very high. But over the life of the well or well platform, the liquid level will go down, water content will go high, and the gas will also go down. The pressure will also go down. But the dimensions of the equipment remains the same across the life, irrespective of the liquid level going up and down. So in that cases, we change the level settings, but diameter and the length remain same. Now you're talking about the earlier questions, like how we define this liquid level. We keep this liquid level same between NLL, HLL, HLL to NLL, and everything same. But generally, people keep some margin between NLL to HLL and NLL to LLL, so that anything, any upset will take sufficient time to reflect in the system, as well as there shall not be any spurious calls all the time. But again, as you correctly said, the intervention time or the response time of an operator, uh, plant's complexity, and the knowledge or the response time or the response behavior of a operator plays a critical role while designing this. But generally, uh, this 10 minutes was just roughly taken, but what I seen majorly in my career, that is 1311. This 3 meter is again divided into 1.5 and 1.5. I guess earlier I told that one.
Yeah, actually, my question was actually was that. So in any case, the height, like I'm considering design for the like different applications and like for the different industries. And
No,
in
no,
any
no,
case, the height of yeah,
no. Suppose if
this
you are
actually
no. Suppose if you are designing a vessel which is having 1 lakh kg per hour flow rate, a mixed flow rate. Someone else might be designing. Suppose you are
yeah.
designing for air. I am also designing for the air, but my flow rates are 10,000 or 10 lakhs kg per hour. So your dimension, my dimensions won't be same, but the terminology or considerations remains the same.
Yeah, actually, there are actually considering like the bottom, the alarms that we have considered, it will remain the standard that we're considering will remain same for all the applications. So
Yes, you consider.
bottom length like below the inlet nozzle, like below the
Yes,
inlet nozzle that we have considered, will almost it will never be changed. I think for any flow rate, like
yes,
diameter will affect
change. Will change.
and
Will
also.
change.
So in this way, if we consider this reference, so the height of a vertical separator will be remain same, irrespective of the diameter. Like height
No,
of
no, no, no,
if
no. We use inlet devices. We use mist eliminators, or sometimes your droplet size, diameter of a droplet size also varies. Some application changes, whether it is a flare gas consider flare knockout drum
yeah,
or compressor knockout
I'm
drum.
totally agree. That depends on the like application is one
Application.
thing,
Yes, because
and application is one
1311
thing.
what we 1311 is the time limit. What we consider is the general one. But if I add, as I mentioned, this diameters, if you can see this timing, this changes based on the application. Whether you are operating a reflex drum, flash drum, compressor, or
Okay,
there might be
okay,
someone.
okay.
Uh, yeah, here you can see if it is surge drum upstream of a fire hydrant. That's what I was telling. Then if you
Hmm.
use 1311 as a same time limit for this drum sizing, then your tube will sense higher heat and they may melt down. So you need to have a
Yeah.
higher liquid content. So you need higher liquid volumes or higher liquid levels in this vessel.
Okay. Clear. Now clear. It is clear.
Yes. So it's not like generalized one. What I told you is the general what I generally it is being considered any separator sizing and all. So best suppose as I said, If the flow is coming from the other platforms, flow is coming from the same platform, but the gas injection same, like there are different additional factors will also come in. So it's better you go through GPSA, Shell DP. That will give you much more idea.
Okay. Other than the design, there is some operation constraint also may be considered for the specific design or specific applications.
Absolutely, absolutely.
Yeah. Okay. Thank you.
Yeah, Abdul Samad, you have also raised. Ab, Abdul Samad, you have a question? Okay, I guess he is not available.
Sir, one common,
Yeah, yeah.
normal query apart from this, if you want to address. Sir, for a PSV, the build-up back pressure is there. Okay, whenever PSV opens,
Okay.
so the PSV discharge line is goes to discharge header, which is common for more than one PSV, the common pipe rack header.
Correct.
So when my one PSV is open and goes to discharge header, so what? How to find build-up back pressure? Just quick overview.
Okay. Suppose if you have a flare tip, then your flare tip
No, sir, not
there is
flat tech.
open to
Okay, okay.
atmosphere. Okay.
Huh.
Open to atmosphere means at the end, suppose your PSV is located at A part and your common line is flowing for 1 kilometer and then it is going to atmosphere. So you know the downstream pressure as atmosphere, that is P2. Then you have to know the length over the 1 kilometer which is flowing and which is changing across the diameter. Suppose your PSV outlet is 2 meter, then 2 inch, then it is connected to 8 inch, then it is connected to 16 inch, and then it is going to atmosphere. Then you have to calculate the equivalent length for all these diameters into one diameter, and then you know the flow rate, or you have to iterate the flow. You know the flow rate of the PSV, then you know the destination pressure, that is atmospheric. Then you have to calculate the P1 for that flow rate and the equivalent length what you have considered or you calculated. So you will be know the P1. So that would be your back pressure.
But sir, if at a time other PSU also open, which is same header of comma discharge, so it will also resist my first PSVs when it opens, na? So it added
Yes,
of
obviously.
that pressure
So that time you have to use flare net. You can calculate this into
as per
Excel as
plan.
well. Flare net. Someone has put into chat as well. Let me. Abdul Samad. Abdul Samad, you can put your query here. About gas holders, we do not do any separator sizing as such for gas holder, but we generally do the gas holder design, that is instrument air holder or utility air holders, that is based on the volumetric flow rate and how much time we need that gas flow rate, like 25 sm cube for 5 minutes or 15 minutes, and based on the pressure, like from 8 bar to the 5.5 bar or something. So in that case, we use the density difference and the time limit for which we want instrument air to be supplied to the plant, and based on that we calculate the volume we need to be stored and we calculate the L by D ratio. There is no low liquid or high liquid separation consideration.
So
So
you
Abdul
said
Samad,
at the starting of your webinar, 10D, 20D. What is meaning of 10D? 10 diameter, 20 diameters.
10 times the diameter of inlet nozzle. 10 times the inlet
Because
diameter
it
of
is also used for friction loss calculations, like 90-degree elbow. So 10D, 20D.
no, 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 no. That is the L by, that is different. This is what we talk about the straight length. Generally, your separators shall not have any bending or any device which causes the friction or pressure change or direction change minimum 10D upstream of inlet device or inlet nozzle.
10D is D means the inlet
Diameter of a
pipe
nozzle.
diameter.
Diameter of a nozzle. Suppose your
Let's
diameter is
suppose
2 inch. or
Huh?
4 inch, then 40 inch
Huh.
from the device, you shall not have any bend.
Okay, thumb rule.
No, it is shell DP
So,
requirement.
okay.
10
So
D,
for
5 D.
friction loss, in a friction loss calculation, that 10D, 20D means what is that?
That is different. That is bending, I guess. That is 5D, 10D, or 2D. That is the piping. That is different. That is short radius, long radius elbow you're talking about.
Yes, yes. Okay.
Yeah, someone Janakala Dhiraj. Yeah, flashing calculations in a control wall is based on the generally the vapor pressure and the enthalpy balance. So you just read about the enthalpy balance across any device. So you will come to know how the flashing has been calculated. Any software program uses the same methodology. So anything you have for separators, will be happy to take. Or else we can stop here. Almost 10:30 p.m. here in India.
There is one from my side actually. Uh, Actually, it was a quite informative webinar regarding separators. So, hopefully, like current scenario is regarding the renewables and all like green hydrogen and green chemicals. So, like could you tell us the specific considerations, some highlighted consideration that we must have to keep while designing the separator for like uh, electrolyzers, like green hydrogen generation? Like the
No,
reason why I'm asking this question is regarding like the generation. There is a co-generation of hydrogen and oxygen together in the electrolyzers, and this is once they are got generated, there is some traces amount of oxygen that is remain in the hydrogen, and the hydrogen's amount remain in the oxygen. And like this is actually explosive. Those recombination possibilities are always there. So both those recombine, like hydrogen and oxygen recombine, then there is a heat. Like there is excessive heat generation and kind of explosive mixture generation possibilities are there. So during the separation, so could you tell us specific consideration, if any? Yeah.
no, we generally don't go into that separation because the molecule carry over ions generally plus and O plus ions. Generally, we don't do any separation sizing for that. Generally, we know for every molecule of hydrogen generated, there are 3 moles of water has been carried over along with it. So we do separator sizing to separate the water. We do not do any separator sizing to separate the molecules like H plus ions and O plus O minus ions. So this has been we generally use other methodologies to keep that concentration low. But generally, yes, we do separator sizing for the water. It has been carried out along with the hydrogen ions it goes through the uh, across the electrolyzers membranes.
Okay. Okay. Reason why actually I was asking this question actually, like while the gas mixture that is generated from the electrolyzer, it is along with the like water itself, and there is oxygen itself. So the oxygen and hydrogen have a different molecular weight, and like specific
No,
gravities are
molecular
different.
into gas form only, right?
Yeah, those are in the gas form, but they have a specific gravity difference as well.
No, gas. How will you separate the gas and methane and air? There is no separator which separates the methane and air.
Yeah, that's you are telling right. Okay. Okay, so there is no possibility as you for the gas considerations you are
Yes,
telling. Like I'm
yes.
actually considering like here we are considering like in a droplet size here, that we are considering the liquid
No,
and gas phase separation. But these are the actually phase differences there actually.
yes.
But for the gases, I was considering the density difference is also there regarding the specific
Density
gravity
difference is
difference
there,
is
but
there.
that is very minimal. You calculate the density of hydrogen at 10 bar and calculate the density of uh, oxygen at 10 bar.
Hydrogen.
So the density difference is
I,
very minimal.
I think it is a quite actually.
Yeah, it's quite, because the molecular weight of hydrogen is 2 and oxygen is 32. So it is, but still we cannot separate the gas from the gas
Okay.
using any
So there
separator.
is no. Okay, so
No,
there is
you
no
have to use
specific
membrane.
inputs for this.
You have to use membranes.
Like we have to go with the PSA only, like you are considering for the
Yeah,
gas separation,
PSA,
like membrane.
PSA or membranes.
Yeah. Okay.
Yes.
I have one question, last question. Actually, this when we are designing separator, this high level to the low level, there is a pressure also varies, right? As the level is increases in the separator, pressure also increases. So whatever the detention time you consider, it
No,
is.
no, 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 no. Liquid is incompressible.
Sir?
Liquid is incompressible.
Ah,
And we are considering this as a continuous process. So feed is coming, vapors are going, liquids are going. So even though suppose your liquid level goes high
okay,
from low liquid level to high liquid, your
okay.
air side is open. Okay, then
Mhm.
the effect of this height change is generally generally 600 mm. So it's
Hmm.
0.6. So the vary you can consider rho gh. So you can calculate how much is the pressure change you can observe.
Okay, okay. So that pressure, yeah, we can convert
No,
into pressure.
negligible,
And
negligible.
okay, okay. Because of the diameter is big.
No, no, it's because of height. If you are
Because of,
having 10,000 meter diameter and liquid height is only 1 meter, then 0.1 is the pressure. Even though if you have a 1 meter diameter and liquid height is 10 meter, your pressure is 1 kg.
okay, okay. Sir, my second question, this droplet size, how will decide? Because this continuously
Sorry,
varying. The the
sorry.
the drop the liquid and gas droplets,
Uh-huh.
micron. You are saying now the to calculate the drag coefficient, there is some dp, the particle diameter.
Yes.
How will estimate this? Is required any software or any
No, 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 no. You have
calculation?
to consider how much particle size diameter you wish to separate. This is up to 150 micron, up to
Sorry, sir,
1000
your
micron.
voice is not clearing, sir. Your voice is
No,
breaking.
no. You have to select while sizing the test. You have to define
Huh.
how much particle diameter you want to separate. Like you 5 microns particle diameter in separator, or up to 1,000 microns. You have to define.
Means
And if you wish to see how much it can separate, though you can use the GPS equation, it will give you. You have to put the dimensions and physical property. It will give you up to what diameter the selected vessel can separate the particle diameter.
in the beginning, when we are before the pre-design, we need to provide a scope of work. In that, we need to mention this particle size, the particle size diameter, right?
Yes, if you require any particular situation. Generally, people use K value where it does not take any diameter consideration in separators. But generally, people define how much percentage of liquid droplets, like in the form of liquid, carry over to the along with the per MMSC of gas, like 7 lb per MMSC of gas, or 150 ppm of liquid carry over, something like that they define.
I'm sorry, sir, your voice was not clearing me. Anyway, no problem.
No, no, no. Generally, if you are
Uh-huh.
sizing any vessel,
Okay,
people define how much separation is required.
okay,
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 that has been there in already design basis or requirement.
okay.
Okay,
Okay, sir. Yeah, understood, understood. Sir, then you said one more word is the nozzle connected with the separator. That is what is the exact word, sir? Separator,
separator nozzle connected with separator. Suppentator.
Suppentator. Ah,
Suppentator is the suppentator is let me if I can find
yeah, yeah. How is image?
suppentator. Let me just find on Google.
Yeah, yeah,
Suppentator in separator. It is the design. found by Shell.
This is
Okay.
proprietary, sir. Is it proprietary?
It's a proprietary, pure proprietary.
Okay, okay.
Pure
And
proprietary.
this helps the reducing the diameter of the equipment.
Height of the diamond, height of the vessel. Here you can see the Separator.
Ah, okay, okay.
So here is the inlet and it has the vents. Here you can see
Okay, okay.
this is coming and it is being divided into smaller sections. So if your 100 is coming, so 50 is going into this side, 50 is going into this side, 10, 10, 10, 10, 5 times or multiple times. I'm just taking raw example. So your rho v square is falling down. So this density difference, like rho v square means indirectly your velocity is going down. So that's how your separation is easy in these cases. So this
Sir,
is the Separator.
yeah, we have this kind of like a sine wave curve type of baffles inside in the vessel, but cleaning was very difficult, sir. This solid salts are accumulating over there, so we
This
don't have
this this is called a Separator.
where, sir?
This is
Ah,
this is the Separator, and generally this is half open pipe, half open pipe.
okay.
Here you can see the Separator. It is reducing the area so that maintaining